Swayam Prabha. Digital India. Educated India.
So, welcome to the class today, and we will just extend what we did in the last class, and we will be seeing how we can extend our technique to solving non-homogeneous ordinary differential equations. Okay. So, we are looking at so here we have talking about a system of the form x dot equals ax plus b. This term b is my non-homogeneity. What do I mean by non-homogeneity? It is something like a source term, okay. It is something which is independent of x, the variable which you are interested in finding, okay. This is non-homogeneity is usually a source or a sink physically. This is the physical meaning, and is independent of the dependent variable, okay. This non-homogeneity can also be, for example, in a CSTR, this non-homogeneity comes from the feed term, what is coming into the reactor, okay. And it can also be a function of time. If something is varying periodically with time, so for example, that could also be. So, basically I am saying this B can be a function of t. It can be a function of the independent variable. The independent variable is t, the dependent variable is x, okay. So, how do I extend whatever we have done so far to solving this kind of a problem? So, again x is n by 1, b is n by 1, and a is n by n, okay. A is an n by n matrix, x and this are n by 1 matrices, n by 1 vectors. So, what we do is the same thing, which is write b of t in terms of the eigenbasis of t ui. And this you know how to find the beta I. If A is self-adjoint, take the inner product with ui. If A is not self-adjoint, take the inner product with Vj bar, like we did before, okay. So, B is a vector. Only thing is this can be a function of time. If this is a function of time, u is independent of time, the time dependency of B I am incorporating in beta, okay, and I can find this. Now, again x of t you write as sigma Ci of t ui. Okay. This is also a vector, I am writing in terms of this eigenbasis. I want x to satisfy this equation, so I write it as x dot of t is Ci dot sigma Ci dot of t ui equals sigma A times sigma Ci of t ui plus sigma beta I of t ui. Okay. Again, you can group all these terms together like we did before, and I get Ci dot of t minus a ui is lambda ui So, I have just done exactly whatever I did earlier. So, I am not writing all the steps. This is Ci dot a ui is lambda I ui, and I am bringing it to the left hand side. I get lambda I Ci ui, okay, and beta I again I am bringing to the left. I get this. Again, the argument is that ui's are independent, and therefore this has to be true for every time, and I get this equation has to be satisfied by the Ci of t. Okay. So, this must be true for all the times and all the i's. Now, again, what is the solution to this equation? So, these are just individual equations for each of this is for Ci, and the solution to this equation Ci of t is 0 t plus now this is a equation, the solution is something you are familiar with. Are you familiar? You can get this using what method? By exactly by using integrating factor, because this is basically a first order equation with some coefficients and the non-homogeneity. Okay. How do we get this? Using integrating factor. Okay. So, I am not going to explain how you get the solution using integrating factor, because you know how to do using integrating factor. So, you should do that and see if you get this. So, each of the Ci of t is known. So, I know Ci of t is given by this, but what I want to do is, so given a particular beta, so what is tau? Tau is just a dummy variable, okay. I am integrating from 0 to t. So, this is just tau is a dummy variable. When I am integrating it between these two limits, I will get a function of time, okay, t. If I let me differentiate this, Ci dot of t is Ci of 0 lambda I e power lambda I t. What I am doing is I am just seeing if it satisfies the differential equation. So, I am just going to differentiate this with respect to time. So, I get that plus okay minus lambda I e power minus lambda I t times integral of this 0 to t e power lambda I tau beta I of tau d tau, and this is I will use product rule, right. So, I need to write this as plus e power minus lambda I t times derivative of this multiplied by e power lambda I t times beta I t. So, I have just differentiated this and to see if I am getting Ci of t. So, if I take e power, okay, clearly this has to be plus Ci of 0 will be is lambda I Ci. Yeah, so this has to be plus, so this will be plus and this will be minus. Okay, so then I get plus here, I get plus here, I get minus here, and I get plus here. Huh? Yeah. How do I get this term? By Leibniz rule, because this is a function of time also, and when you differentiate this with respect to time, so what I have done here is just to verify if this is where the plus and minus sign, so this is fine. Pardon me? Yeah, now the signs are correct. Yeah, you should have told me that before, man. I know, it's okay. Thank you. So, anyway, so this is the right solution, okay? But you guys have to know, I mean, I'm not remembering most of those things. So, I just checked if this solution satisfies the differential equation. So, this is the derivative, this is product of two functions because this is also a function of time. So, derivative of the first function, what about the derivative of this? Because the limit is here, use Leibniz rule and you get this, okay? And I think this is fine. So, this goes to 1, this is plus beta I. Yeah, I am happy with that. So, now there is what we have to figure out is the Ci of 0 in this. So, how do we find that? From the initial condition, okay. So, x of t equal to 0 is x naught. This is also an initial condition which is given to me. So, I need to put x of t is sigma Ci of t ui at t equal to 0. This gives me x naught equals sigma, put t equal to 0, this becomes 1, put t equal to 0, this becomes 1, this becomes 0 because now the limits are from 0 to 0. So, I get Ci of 0. Okay, and now you know how to find out Ci of 0 by using the orthogonality or the bi-orthogonality. Okay, so find Ci of 0 using I'll put bracket by, and once I know Ci of 0, I can substitute it here, find Ci. Once I know Ci, I can substitute it here and find x. Okay. So, that is the method. So, what we have done is basically extended whatever we have done to non-homogeneous equations. So, what I thought I will do is spend a little bit of time trying to explain to you the kind of a geometric basis of whatever we are doing. This approach of trying to find solutions in terms of eigenbases, eigenvectors as a basis, okay, what exactly are we doing? So, again trying to put different things that you may have learned in one common perspective. So, consider, so the, I will just call this geometric understanding of our approach. Okay. So, if you take a vector B, it is of the form B1 B2 Bn. Okay, B1, B2, Bn subscripts represent the different coordinates of the vector B, and in terms of the standard basis, I can write this as B as B1 E1 plus B2 E2 plus B3 E3, etc. What is the standard basis? E1 is 1 0 0, E2 is 0 1 0. Okay. Just for your reference, I am just writing this down. Okay, that is how we are writing it. Now, if I take the same vector B and write it as sigma beta I ui, where ui are the eigenvectors now. Okay. So, I am using a different basis to represent the same vector. So, here I use ei, here I am using ui. So, now I have B1, B2, B3 etc. Okay, equals beta 1, and this is subscript 1, superscript 1, 2 1 2, U3 1. Is this clear? The subscript denotes the coordinate, the superscript denotes the vector. Okay, this is the first vector, superscript is 1, subscript is the coordinate, coordinate is the subscript, plus beta 2 times U21, U22, 3 etc. Okay, I am just showing it for 3 by 3 case just to keep things simple, but you can easily see how it goes to the n dimensional case. Okay. So, this is what we are doing, same vector B1, B2, B3, I can write it like this, I can write it like that. So, now what I am going to do is write this as the first element is beta 1 U11 plus beta 2 yeah. So, I just did the matrix multiplication. Okay. I can write this as P times beta, or yeah. So, basically I have just written B like this in terms of the eigenbasis, expanded this out, ui's are the eigenvectors, okay, and these vectors have this kind of representation. I am just writing it like this. And what is P times beta? What is P? P is a matrix which contains the eigenvectors as columns. So, P has the eigenvectors as columns. And beta is beta 1, beta 2, beta 3. Okay. So, if you multiply this, you will get beta 1 u11 plus beta 2 u21 plus beta 3 u31. You can check it out. Okay. So, basically what I am trying to tell you is that B is P times beta. And what is P? B is a representation of the vector in the classical basis, EI basis. This is representation in the EI basis, and this is the representation in UI basis, and this has matrix with eigenvectors as columns. So, what are we doing? So, I will just explain with respect to one example, you can understand it. So, when I solve Ax equals b, what you have done so far is always solved it in the basis of EI. Okay. You have always solved the basis of EI, and then you are stuck with a system of coupled equations. So, basically if we use EI as the basis, equations are coupled. Okay. But now I want to, I don't want to use EI as a basis, I want to use UI as my basis. I want to represent X, both B and X we want to represent X and B with UI as the basis. So, if I want to write it as with UI as a basis, B will be in this basis P times beta. Okay. So, I am going to write this as P times beta, and AX I am going to write it as this also I have write as P times X dash. When this is the EI as basis, what is the relationship between this and writing it with UI as a basis? X is B is P times beta, that is what I have written, P is B times beta. Similarly, X also has to be represented in the same basis, okay, then only I can talk, same base I am using. So, this also I am writing as P times X dash is when UI is the basis, okay, this is when UI is the basis. Okay. Beta dash is when UI is the basis. This is also for UI as the basis. So, I am going to multiply both sides by P inverse. P inverse AP X dash is equal to beta, because P inverse P is I. Now, I do not know how many of you know there is something called a similarity transformation. People are aware? Heard of it? Yes, no? Yeah. Basically, similarity transformation tells you that this P inverse AP is nothing but a diagonal matrix with the eigenvalues on the diagonal. Okay. So, basically P inverse AP is nothing but D from summation, and D has lambdas on the diagonal, and all other terms are 0. Okay. So, now x dash multiplied by, I have lambda 1 0 0, lambda 2 0 0 0 0, lambda 3 equals beta 1, beta 2, beta 3. So, what does this mean? It means the first coordinate x1 dash is beta 1 divided by lambda 1, and so xi dash is beta I divided by lambda I. Okay. So, what have we done by doing all this basis change? We have basically decoupled the equations, because now I only have the diagonal entries. So, what was originally a system of coupled equations, now they are decoupled, because in this new eigenbasis, this first coordinate depends only on the first, second depends only on the second, because only diagonal elements are there. So, we have decoupled the equations in this eigenbasis. That is the point I am trying to make, and because of which I am able to do our approach, which I am claiming superior. So, this transformation, this writing things in terms of eigenbasis is basically making a coupled system of equations a decoupled system, and I can solve one equation at a time, which is what I have done. Okay. So, now that I have x dash, how do I find the actual thing? So, this is, so given, so this x dash is the coordinates. So, x dash, x I dash is nothing but beta I by lambda I. Okay. These are the x in the eigenbasis. So, I want it in my original 100 basis. X, remember, is basically sigma xi dash ui, which is what we got, beta I by lambda I ui. So, those are the coordinates in the basis. So, these are the coordinates in the eigenbasis, the coefficients, and so when I want to get the actual solution, I have to do this. Okay. So, I mean, I just wanted to make you aware that this concept of similarity transformation, where we are converting matrix to a diagonal form, is what we have used when we are doing this representation in terms of eigenbasis, and which helps me solve one equation at a time, and then I go back and find the solution. Okay. So, that is the perspective I wanted to give you. It is not just doing solving a problem, but understanding a different aspect of this method. Okay. So, those of you who want to, if you are not aware of similarity transformation, I suggest you go and read about it, because it is a very classical thing in linear algebra. Okay. So, let us see, consider this batch reactor. And we will keep our lives very simple. A giving B, this reaction is going on inside this batch reactor, okay, and we will keep all reactions first order. So, we will take this, let us say 1 second inverse and 2 seconds inverse, just I can do it, or maybe just do K1 K2 man, let us keep it as K1 and K2. Those are the rate constants. So, I have a batch reactor in which this reversible reaction is going on, okay, and when it comes to a batch reactor and a reversible reaction, what are we interested in? We are interested in what is going to happen finally at time t equal to infinity, what is going to be the equilibrium concentration in my reactor, okay. So, to cut a long story short, we need to write the equations for A and B. dCA by dt will be minus K1 Ca plus K2 Cb, and dCb by dt will be K1 Ca minus K2 Cb, okay. These are the differential equations which tell me how the concentration of A and B change with time inside my reactor, okay. So, at equilibrium what happens? There is no change with respect to time. So, I put derivative equal to 0, okay, and I get minus K1 K2, okay, let me write it this way, minus K1 Ca plus K2 Cb equals 0, K1 Ca minus K2 Cb equals 0, and I can write this in a vector form, minus K1 K2 K1 minus K2 CACB equal to 0. So, I do have two equations in two unknowns, okay, but it turns out that these two equations are dependent on each other, they are the same actually. I do not have an independent equation, right. These two equations are exactly identical. That means one of the eigenvalues is 0, right. These two equations. So now let me try to do this thing in a sensible way. So that, okay, so basically these two equations are identical, i.e. dependent, and therefore, if you look at this matrix A, I will just put this as minus 1, I will take the same values which I wrote earlier, which I removed, okay, it's 2, this is matrix A, assuming K1 equals K2, K1 equals 1 and K2 equals 2, just so that things become clear. So, what are the eigenvalues of this matrix? If you look at the eigenvalues of this, clearly one eigenvalue will be 0 and the other eigenvalue will be -3. Okay. So, I am interested in the eigenvalue corresponding to eigenvalue equal to 0. So, what is the eigenvector corresponding to eigenvalue equal to 0? Corresponding to lambda equal to 0, the eigenvector is going to, what is that? Okay. x1 minus x1 plus 2x2 equals 0, or x1 minus 2x2 equal to 0. So, I am going to substitute, put x2 equal to 1, x1 equals 2, and so my eigenvector is of the form 2, 1. Okay. Now, if you go back to that ordinary differential equation system that you had, x dot equals ax, but x is CACB, I mean x is CACB, A has the K1, K2, okay. I wrote down the two equations for CA, so and CB, so that is what I am saying. So, what will be the solution, what will be the form of the solution here? The form of the solution here, I am not solving it, you guys can solve it, will be Ci of t ui, which is Ci of 0 e power lambda 1 t u1 plus C2 e power lambda 2 t u2. Since I have a 2-dimensional system, since I have a 2 by 2 matrix, dimension is 2, my summation is only over 2 terms, okay. If you go back to what we did, this is the solution for x dot equal to ax. C1 0 e power lambda 1 t u1 plus C2 0 e power lambda 2 u2. You have to calculate what is u1, u2, you have to calculate all of this. So, this is the eigenvector for lambda equal to 0, this is the eigenvector for lambda equal to 3, lambda equal to minus 3. So, basically lambda 2 is minus 3 and this lambda 1 is 0. So, as t goes to infinity, this is not going to contribute because e power minus infinity will be 0, okay. So, as t goes to infinity, x of t will be Ci of 0 and this is lambda 1 is 0 anyway. So, that is 1 u1, okay. So, it will be of the form C10 2 1 because the eigenvector corresponding to lambda equal to 0 is 2 1, okay. And this eigenvector is something, I mean I am not right now interested in it because I am only interested in the equilibrium. I am interested only in the equilibrium, e power lambda it does not contribute, so that goes off, okay. If you are not interested in the equilibrium, you want to find the full how it changes with time, then you have to worry about this guy. The point is the eigen vector corresponding to lambda equal to 0 tells me, has a physical meaning in this problem, which is the ratio of the concentrations. It tells me the ratio of the concentrations. It do not tell you the actual concentration. Okay. So, point is the eigen vector concentrations at equilibrium. I know that the ratio is 2:1. I do not know what the actual concentration is. Okay. If you want to find what the actual concentration is, you need some additional information. This additional information is coming from the initial condition, because I have to use at time t equal to 0 what was my initial concentration, which is x, and then find out Ci of 0. Okay. Then I can find what the equilibrium concentration is, actual concentration is. To find the actual concentration, we need more information. This comes from the initial condition x naught, because then I can put x naught equals C1 of 0 U1. Okay, and I can use orthogonality and all that to find out C1 of 0. Oh, yeah, yeah. I guess at time t equal to 0, I must put the other fellow also, no, C2 of 0 U2, because I need to use the full form. I need to use the full form at t equal to 0. So, to find this is x naught. To find Ci of t, I will use orthogonality, by orthogonality, whatever it is, and find C1 of 0. Okay. So, find C1 of 0. Once I find C1 of 0 at t equal to infinity, I can calculate what the actual concentration is. Okay. From this, we can find the actual concentration. So, the extra piece of information about the initial condition is important if you want the actual concentration. If you only want the ratio of the concentrations, then you do not need the thing, you are just interested in what the ratio is. Okay. And this is typically true because this particular system is a closed system, it is not exchanging mass to the environment. Okay. So, this is a characteristic of a closed systems. So, I will give you just one more example for you to understand that in a different context. Supposing you have an insulated vessel and let us say you have water here, and then you have a hot ball and water is let us say cold. Okay, I am keeping all temperatures less than 100 degrees. Hot is so water is let us say at 20 degrees, the ball is at let us say 70 degrees, and this is in an insulated environment. Now at time, as you wait for a sufficiently long time, my question is what is going to be the temperature? So the first thing you will say is that temperatures have to be equal, because after some time heat transfer will not take place between the two, between the solid and the liquid, and there is no heat transfer outside. So point is, let us say this hot ball is at 70 degrees and this is at 20 degrees. So I am not allowing boiling and all that. Okay. So as T goes to infinity, the temperatures of the ball and water will be equal. But what is the actual value? I won't know. I will know what the actual value is only if I use the information about the initial condition. What is the temperature of the ball and what is the initial temperature of the ball, what is the initial temperature of the water, because then I will say heat loss by the ball is equal to the heat gained by the liquid. Okay. So I need that information about that initial condition. Only then I can find what the actual temperature is. So here, when we want the actual temperature, we need info about the initial condition. Then I can say heat loss by the ball equals heat gained by liquid, and this again is a closed system because there is no exchange with the environment. Okay. So again I need that initial information, like in the batch reactor I needed that initial information. What is the reactant concentration in the beginning? Only A, only B, and then I found out what the actual value is. Okay. So when this business of the, so two things, that eigenvector in this problem, basically what I am trying to tell you is it can also have a physical meaning. It is not just a mathematical entity. It can have the eigenvector is telling you something about the ratio of the concentrations. It is telling you a ratio of the temperatures. Okay. And when you are talking about a closed system where lambda equal to 0 is an eigenvalue, but what the actual value is you are not able to predict. For that you need this information about the initial condition, then you can go ahead and say that this is the actual concentration. So whatever we have seen here also has physical meaning. It is not just mathematical quantities that you are doing, eigenvector and all that. Depending upon the physical problem that you are solving, your eigenvector can have a physical meaning. That is the point I want to make. Okay. Thank you.